Quantum electrodynamics was built to explain the single, isolated photon. Optics, historically, was built to explain the continuous, macroscopic laser beam. For decades, calculations in quantum electrodynamics relied almost exclusively on a specific set of mathematical states known as the stationary states of the non-interacting field. These are the n-photon states, also known as Fock states, written in direct notation as a ket with the integer n. They represent a system containing a precisely counted exact number of photons. This basis is perfectly suited for perturbation theory. When calculating subatomic interactions, where the photon count changes by exactly 1, the math holds up. That mathematical precision collapses at the scale of macroscopic optics. A simple beam of light contains an intrinsically uncertain, massive number of photons. Forcing a macroscopic field into exact photon number states removes all information about the phase of the wave. Without phase information, the field cannot represent an oscillating wave, making the transition to the classical limit mathematically impossible. In 1963, physicist Roy Glauber published a solution. He proposed discarding the n-photon basis entirely for the study of optical fields. In its place, he adopted a different set of basis states, which he termed coherent states. These states allow the quantized field to retain the properties of an oscillating wave, providing the mathematical link between individual particles and classical optics. By constructing a specific density operator known as the P representation, we can trace the exact mathematical lineage, showing how classical electromagnetic waves emerge strictly from quantum field statistics. This is a phase space diagram, plotting a field mode's coordinate q on the x-axis against its momentum p on the y-axis. We use this to visualize quantum states geometrically. The exact center of this plane represents the quantum vacuum, or the ground state, written as 0 in a ket. The state is drawn as a blur because the field cannot be completely empty. It contains 0-point fluctuations, an inherent physical uncertainty equal to 1/2 h bar omega. Glauber defines the coherent state mathematically as the right eigenstate of the photon annihilation operator, such that applying the operator A to the state yields the complex eigenvalue alpha. Physically, this state is generated by applying a unitary displacement operator directly to the vacuum ground state. This shifts the probability density radially outward to a specific complex coordinate. Time evolution is simple. It orbits the origin at a constant frequency omega. As it orbits, the shape of the wave packet remains perfectly rigid. It does not spread out or dissipate over time. It maintains the minimum possible uncertainty product permitted by quantum mechanics. Delta P times delta Q equals exactly 1/2 h bar. Because this displaced probability density oscillates smoothly and retains its rigid formation, it behaves exactly like a classical harmonic oscillator. The traditional n-photon states possess a highly convenient mathematical property. They are perfectly orthogonal. A state of 2 photons and a state of 3 photons are mutually exclusive. Coherent states lack this convenience. When plotted near each other in the complex plane, the blurred edges of distinct coherent states physically overlap. Because of this interference, their scalar product is not 0. They are non-orthogonal, and the overlap magnitude decays exponentially as they separate. The concept of non-spreading wave packets was familiar to early physicists, having been documented by Erwin Schrödinger in the 1920s.
But because the states are not mutually exclusive, physicists generally ignored them as a viable basis for expanding arbitrary fields. The math appeared too messy. Glauber proved that while coherent states are not orthogonal, they do form an overcomplete set. Any arbitrary quantum state of the radiation field can be uniquely expanded in terms of them. To utilize this completeness, the discrete grid of stationary states must be replaced by a density operator. Glauber defined the density operator as the integral of the projection operator over the complex plane, multiplied by a weight function, p of alpha. The weight function, p of alpha, dictates the statistical distribution of the coherent states within the field. This side-by-side comparison shows a classical probability distribution of field amplitudes on the left and the Glauber p of alpha function on the right. They look visually identical. This visual similarity led to immediate disputes. Physicists like E.C.G. Sudarshan argued that the existence of this function proved a complete equivalence between classical and quantum photon statistics. That equivalence is mathematically false. P of alpha is an intrinsically quantum mechanical structure. It is a pseudo-probability. Depending on the quantum state, P of alpha can become highly singular or take on negative values, something impossible in classical statistics. P of alpha only behaves as a true positive classical probability distribution in the limit of massive amplitudes, where the value of alpha is much greater than 1. The limitations of P of alpha mathematically define the exact boundary where quantum mechanics crosses into classical physics. We can apply the P representation framework to macroscopic physics to observe its predictive power, starting with chaotic or thermal light. A macroscopic source, like a gas discharge tube, consists of millions of independent stationary atomic emitters. As emitters radiate, outputs superpose in the quantum field, adding up as a two-dimensional random walk of complex displacement vectors. Driven by the central limit theorem, this massive superposition smooths into a wide Gaussian probability distribution centered at the origin. This specific Gaussian weight function defines chaotic light. When you substitute the Planck distribution for thermal excitation into this equation, it maps perfectly to the classical theories of thermal radiation. Glauber's framework derives the macroscopic Planck blackbody distribution strictly by calculating the geometric statistics of the underlying quantum field. If thermal light and a laser can be engineered to share the exact same energy spectrum, what differentiates them at the quantum level? The formal definition of coherence requires the perfect factorization of the field's correlation functions, denoted mathematically as G subscript n. A pure coherent state, resembling an ideal laser, factorizes perfectly. It satisfies the condition for coherence to an infinite order. The Gaussian state we derived for thermal light behaves differently. When you calculate the higher-order correlations for thermal light, an inherent n factorial term appears in the equation. That term prevents perfect factorization. Imagine passing chaotic blackbody radiation through an ideal filter, stripping away all frequencies until you isolate a single perfectly collimated wavelength. The filtered light achieves first-order coherence, meaning it has a perfect spectrum. But the presence of the n factorial term guarantees a representation proves that coherence is an inherent feature of the field's quantum statistical geometry, distinct from a beam's classical spectrum.